Six Sigma ET uses a multi-level, unstructured, staggered grid. This method utilizes typical structured grid advantages such as robustness and accuracy through staggering of variables, and combines it with the traditional advantages of an unstructured grid. This allows us to generate a grid that solves at lightning speed with unprecedented scalability. Here we see a grid generated for a PCB where all layers as well as traces are explicitly modeled. The gridding in ET is automatic, with intelligent grid rules for each of the objects. For example, generating a grid for a PCB will automatically account for the inflation layers above and below the PCB. In this example, we will see how ET generates grid for the same object with varying sizes. We will add two different types of heat sinks with two different dimensions. First, we add an extruded heatsink and pin fin heatsink to components of different sizes and generate the grid. As you can see, the automatic grid generated accounts for the boundaries on either side of the heat sinks with just enough grid between the plate fins to capture the jet and at least one cell to account for the thickness of the fin. From the top, you can see that the grid captures even the tricky staggered arrangement quite effectively. This automated process, developed through years of experience and research, enables any user to achieve accurate results with minimal effort. Let's see how ET handles the grid for imported geometries. Though there are multiple ways to import a CAD model, the simplest way is to have it replace the heatsink as shown here. An advantage of replacement is that the imported CAD now assumes the intelligence of the replaced heatsink, including retaining the same material properties. We will now generate the grid for this imported CAD heatsink. ET generates the grid for this skewed heatsink automatically using the built-in intelligent grid rules for heatsinks. Let's now import a more complicated CAD shape into ET. Here we can see the default grid generated for this shape. The nuts and bolts in this model can be simplified, or if needed, modeled as approximate. ET's gridding functionality is flexible because it adapts to any geometry automatically, while providing the user the ability to control the level of detail by either increasing or decreasing the amount of grid. In another example, we will see how ET generates the grid for imported geometry. ET grid generation accounts for the shape and the conduction of the imported CAD automatically, and in cases where the CAD requires more grid, we can add it easily through the property sheet without changing any of the global settings. ET's solver is very powerful and can handle grid cells with high aspect ratios. However, if you want to limit grid size based on aspect ratio, you can do so through Solution Control, Grid, Apply Smoothing. Here you can change the aspect ratio to whatever value you need. Based on this constraint, the solver will generate the grid accordingly. Another way to customize the grid for a model is by adjusting the target value under the Solve ribbon. The target value allows the user to set a suggested grid size specific to the RAM currently available on your machine. The inherent grid rules within the solver can, however, override this number. The software will select a value between the chosen target and the minimum required grid cell size needed for acceptable accuracy. Another way to control grid in ET is to use grid control. Grid control enables the user to carry out gridding for complex models efficiently. Grid controls can be added to any object in the model tree. For example, if you want to increase the grid within a chassis, you can do so by right-clicking that object and selecting New Grid Control. Once a grid control has been added, it can be modified in the property sheet. Here you can choose to add grid controls along the X, Y, or Z axes, or all three. Also, by deselecting the Size from Parent checkbox, you are able to resize the area and move the grid control around. You can customize the construction of the grid by selecting from the drop-down, or indicating the number of cells directly. ET's flexible and scalable multi-level unstructured grid addresses the challenge of multi-fluid applications through geometry-based gridding. For this imported CAD geometry, we will add a grid control and select Geometry-Based Gridding. As seen, the grid can be applied to the solid or the fluid of the selected geometry, or to both. If the Inflate to Fluid checkbox is selected, the property sheet will generate multiple options for grid generation. These powerful gridding features, coupled with Six Sigma ET's revolutionary solver, make it the most complete and powerful CFD simulation tool for the electronics industry.